Hello students, today we are going to learn about Riemann integral, when it exists and what are the conditions for a function to be Riemann integrable. Coming to this Riemann integral, it is developed by Bernard Riemann and he is from 17th September 1826 to 66 July, who is a German mathematician. He contributed a lot to mathematics subjects like analysis, number theory, differential geometry. In the field of real analysis, he mostly is known for the development of integration or which is known as Riemann integral, and he worked on Fourier series also. Before going to study about Riemann integral, let us start with the non-empty subsets of set of real numbers. We know that any non-empty set of real numbers is known as an aggregate. Generally, we denote aggregate by set notation capital S, like natural numbers, set of integers, rational numbers, these are all aggregates of the set of all real numbers. So, we will talk about boundedness of aggregates of the set of real numbers. We say that an aggregate S of R is said to be bounded above if there exists a real number k1 such that x less than or equal to k1 for every x belongs to S. That means, every element of S is less than or equal to some real number k1. Then we say that k1 is upper bound of S and the aggregate S is said to be bounded above. Whenever it is bounded above, there are many real numbers greater than k1 and less than k1 also. So, we can think about least of all these numbers. So, we define a real number u called a supremum of S if u is an upper bound or and any number less than u is not an upper bound of S. So, we know about this supremum, all these we have studied in earlier chapters. Least upper bound or supremum is an upper bound, which any number less than that is not an upper bound, but if u is an upper bound, any number greater than u is also upper bound, but less than u is not an upper bound. So, how you explain it symbolically? Suppose if u is a supremum of an aggregate S, then any small epsilon greater than 0, u minus epsilon is not an upper bound of S. That means, there exists at least one x belongs to S such that x greater than u minus epsilon. If u is an upper bound, then x less than or equal to u. If x u minus epsilon is not an upper bound, then definitely x is greater than u minus epsilon. So, what is our conclusion? Whenever u is a supremum, we have u minus epsilon is less than x less than or equal to u. Next, in the similar manner, we define lower bound, or we say that an aggregate S is said to be bounded below if there exists a real number k2 belongs to R such that x belongs to S implies x greater than or equal to k2. Here that means every element of S is greater than this k2 and k2 is the minimum element, or we call k2 as a lower bound of S. If k2 is a lower bound, any number less than k2 is a lower bound, but greater than k2 is not a lower bound. So, in such case we go for greatest lower bound or infimum. A real number v is called an infimum of S if v is a lower bound of S and any number greater than v is not a lower bound of S. So, here whenever v is an infimum, like above, we can have an element x of S such that v less than or equal to x less than V plus epsilon. Dear students, here you have to remember two things to learn about Riemann integral. What are they? We have element is less than the supremum and supremum is less than or equal to upper bound. Similarly, you have element infimum is greater than the element. Okay, and here lower bound means there exists x belongs to S such that V less than or equal to x strictly less than V plus epsilon. So, we say that an aggregate is said to be bounded if it is both bounded below and bounded above. That means there exists real numbers k 1 and k 2 such that for every x belongs to S, k 2 less than or equal to x less than or equal to k 1. In such case, we say that S is bounded. Here what we have to do? Remember 2 points. You have element is less than the supremum is less than the upper bound. You have element is greater than the infimum is greater than the lower bound. If you remember these two concepts, you can define Riemann integral very easily. So, before starting to define this Riemann integral, we go for upper and lower Riemann sums. For this, we start with a partition. Suppose f is any non-negative function defined on closed interval a b. What do you mean by partition of a b? That means suppose there exists points x naught, x 1, etc., x n which lie between a and b, satisfying the condition a equal to x naught less than or equal to x 1 less than or equal to x 2 less than or equal to and so on, x n minus 1 less than or equal to x n equal to b, then we write the set of all points x naught, x 1, etc., x n, these are all called partition points of P. That means these n plus 1 points are partition points and the subintervals x naught, x 1, x 1, x 2 and so on x n minus 1 comma x n, these are called segment of the partition P. And what is the rth subinterval? We denote rth subinterval by IR, which is a closed interval xr minus 1 comma xr, which is denoted by IR and its length is denoted by x suffix r minus x suffix r minus 1. So, if you consider the maximum of lengths of subintervals, the maximum of lengths of subintervals is nothing but norm of the partition P. So, after finding the partition, what we will do is we consider infimum and supremum of the function f in each of the subintervals IR. That means, let capital M comma small m be the supremum and infimum of f on closed interval a b and capital MR comma small mr be the supremum and infimum of f on IR for r is equal to 1 to n. Now, we will form the sum m1 delta 1 plus m2 delta 2 so on mr delta r. What is delta 1, delta 2, etc., delta r? These are the lengths of the subintervals. Delta r is equal to xr minus xr minus 1. So, we call the sum sigma r is equal to 1 to n mr delta r, small mr delta r, where mr is the small mr is the infimum of f on IR. This is known as lower Riemann sum or lower Darboux sum and we denote this as LPF. So, what is LPF? LPF is nothing but sigma r is equal to 1 to n small mr delta r. Similarly, we define the sum capital M1 delta 1 plus capital M2 delta 2 so on mr delta r, which is nothing but sigma r is equal to 1 to n capital mr delta r. This is known as upper Riemann sum or upper Darboux sum corresponding to the partition P. See here, if you take any closed interval a b, for example, you take 0 comma 1, the closed interval 0 comma 1. Suppose you take the partition points 0, 1 by 2 comma 1, then there you will get two subintervals 0 comma half and then half comma 1. Similarly, you can take partition like this also 0, 1 by 4, 2 by 4, 3 by 4, comma 1. So, you can form subintervals. Now, after defining LPF and UPF, UPF is upper Riemann sum, LPF is lower Riemann sum. Now, here we define the oscillatory sum. Oscillatory sum corresponding to the partition P is denoted by omega Pf, which is nothing but UPF minus LPF. That means sigma r is equal to 1 to n capital Mr minus small mr into delta r. That means capital Mr is supremum of f on IR, small mr is infimum of f on IR. Now, we are see what do you mean by this set of all UPF and LPF. So, according to the definitions of UPF and LPF, now we are going to prove that the set of all lower Darboux sum are bounded above, that is the set of all LPF is bounded above, and the set of UPF such that P belongs to finitely many partitions of AB is bounded below. So, from this what we will do, we know from the completeness property, we know that the set of all real numbers or the subset of real numbers which is bounded above has a supremum and which is bounded below has an infimum. So, R satisfies completeness property. So, for this what we will do, for a set of all LPF will have a supremum and UPF will have a infimum. If this supremum of LPF is equal to infimum of UPF, then we say that the function is Riemann integrable. For this we notate, we give the notation upper integral a to b f of x dx and lower integral a to b f of x dx. For this, let us see why this LPF is bounded above and this UPF is bounded below. Here you are taking all the points small mr, capital Mr between small m and capital M. Why? Because you have small m is the infimum and capital M is the supremum of the function f in the interval a b. So, what does it follow? You have m less than or equal to small mr less than or equal to capital Mr less than or equal to m. Is that clear? Here you have delta r is length of the interval cannot be negative. So, delta r is greater than 0, you multiply that relation with delta r. So, what you are going to get, small m into delta r is less than or equal to mr into delta r is less than or equal to capital Mr into delta r is less than or equal to capital M, and take sigma for this inequality, which will give you sigma r is equal to 1 to n m into delta r is less than or equal to sigma r is equal to 1 to n small mr delta r is less than or equal to sigma r is equal to 1 to n capital Mr delta r less than or equal to sigma r is equal to 1 to n capital M delta r. Students, here r is equal to 1 to n small mr delta r is your LPF and sigma r is equal to 1 to n capital Mr delta r is your UPF. So, from that relation and sigma r is equal to 1 to n delta r is b minus a. Why it is b minus a? What is the sigma r is equal to 1 to n delta r? It is delta 1 plus delta 2 so on delta n. So, that will give you b minus a. You have small m into b minus a is less than or equal to LPF less than or equal to UPF is less than or equal to capital M into b minus a. So, from this equality what does it follows? Your LPF is less than or equal to capital M into b minus a and UPF is greater than or equal to small m into b minus a. That means, what do you mean by that? You have for every partition P of AB, you have LPF is less than or equal to capital M into b minus a. That means, capital M into b minus a is the supremum, that means it is upper bound of the set of all LPF for finitely many partitions of AB, and small m into b minus a is lower bound of the set UPF such that P belongs to phi of AB. That means, for finitely many partitions of AB. So, by making use of this fact, we are going to define lower Riemann integral and upper Riemann integral. What is, how you define lower Riemann integral? It is nothing but supremum of all LPF, supremum of all LPF such that P belongs to finitely many partitions of AB. So, that is denoted by integral a to b, lower integral a to b, because we do not read it as a bar, it is lower integral a to b f of x dx. And upper Riemann integral, how you define? It is infimum of UPF. Now, if the supremum of LPF is equal to infimum of UPF, that means lower integral a to b f of x dx is equal to upper integral a to b f of x dx, then we say that f is Riemann integrable on AB. And we say that integral a to b f of x dx, that is common value of upper integral and lower integral, is called Riemann integral of the function f on AB. Friends, now from these definitions, what does it follow? You see here, always small m into b minus a is less than or equal to lower integral a to b f of x dx is less than or equal to upper integral a to b f of x dx. So, here always you have immediately after defining Riemann integral, these are the consequences. Lower integral a to b f of x dx is less than or equal to upper integral a to b f of x dx. That means, you have, see here I told you here element is less than or equal to the supremum. So, what is the relation between LPF and lower integral a to b f of x dx? Here LPF is less than or equal to lower integral a to b f of x dx. And also you have, what is the relation between element and infimum? You have infimum is less than or equal to element, infimum is less than or equal to element. That means, integral upper integral a to b f of x dx is less than or equal to UPF. I told you first at the beginning only, you have to remember like this, element is less than the supremum and infimum is less than the element. So, finally, what you have, LPF is less than or equal to lower integral a to b f of x dx, which is less than or equal to upper integral a to b f of x dx, which is less than or equal to UPF. Or in other words, we can say small m into b minus a. I told you what is m into b minus a, that is lower bound. You have m into b minus a is less than or equal to lower integral a to b f of x dx is less than or equal to upper integral a to b f of x dx is less than or equal to capital M into b minus a. You have supremum is less than the upper bound and lower bound is less than the infimum. Now, see, after defining, let us see how you find LPF and UPF for a given function. Let us discuss one example. Consider f of x equal to x square on interval 0, 1 and partition you take it as 0, 1 by 4, 2 by 4, 3 by 4, 1. Let us compute LPF. What is LPF? To find LPF, you take subintervals. What are they? I1. I1 is interval 0, 1 by 4. I2 is 1 by 4, 2 by 4. I3 is 2 by 4, 3 by 4. And I4 is 3 by 4, 1. So, what is the length of interval? Length of the each interval is 1 by 4. You can observe clearly, delta 1 equal to delta 2 equal to delta 3 equal to delta 4, which is 1 by 4. Now, let us find infimum and supremum of f of x. What is f of x here? X square. So, m1 is 0 square. What is the small m2? It is 1 by 4 whole square, and m3 it is 2 by 4 whole square, and m4 it is 3 by 4 whole square. So, what is minimum here? You have small m1 is 0, m2 is 1 by 4, m3 is 2 by 4, and m4 is 3 by 4. That is the first point of the subinterval. m1 is 0 comma 1 by 4. So, what is the minimum value? 0. m2 is 1 by, it is the minimum value of 1 by 4 comma 2 by 4, like that. Now, you find out LPF, which is m1 delta 1, small m1 delta 1 plus m2 delta 2 plus m3 delta 3 plus small m4 delta 4. So, you calculate this, you got it as 7 by 32. So, if you take one more interval, you will get another LPF. If you take number of intervals, so every closed interval can be partitioned infinitely many ways. So, you can form the set of all LPF. Similarly, you calculate capital M1. What is the capital M1? Is 1 by 4 whole square, and capital M2 is 2 by 4 whole square. That means, what is capital M1 here? This is the maximum value of the first interval. Capital M2 is maximum value of second interval. Capital M3 is maximum value of third interval. So, after finding M1, M2, M3, M4, calculate simple multiplication only. What is UPF? It is capital M1 delta 1 plus capital M2 delta 2 plus capital M3 delta 3 plus capital M4 delta 4. So, this is your UPF. If you observe carefully, definitely your LPF is less than or equal to UPF. Now, we are going to study when this Riemann integral exists. What is the necessary and sufficient condition for a Riemann integral to exist? Before that, we will have, I told no, while defining infimum and supremum, supremum is less than the upper bound, element is less than the supremum, supremum is less than the upper bound. Okay. You have infimum is greater than the lower bound and element is greater than the lower bound. So, keeping these points, before going to prove the necessary and sufficient condition for a function to be Riemann integrable, we are going to state one theorem called Darboux theorem. What does it say? Suppose epsilon greater than 0 is given any positive number. Then there exists delta greater than 0 such that UPF is less than upper integral a to b f of x dx plus epsilon by 2, and LPF is less than lower integral a to b f of x dx minus epsilon by 2, or you can take epsilon also, because epsilon is a small positive number. This follows from the result. See, after defining upper bounds and lower bounds, I told you here, if u is supremum, then u minus epsilon is not an upper bound. So, always you have u minus epsilon less than x less than or equal to u, and also v less than or equal to x less than v plus epsilon whenever v is a lower bound or v is an infimum. So, using that, we can have UPF is less than, UPF is element, element is less than the supreme, element is less than supremum. So, UPF is less than upper integral a to b f of x dx plus epsilon by 2. Students, do not forget here what is upper integral a to b f of x dx? It is infimum of UPF, it is infimum of UPF. What is lower integral a to b f of x dx? It is the supremum of LPF. So, now the function f from closed interval a b to r is said to be Riemann integrable if and only if for given epsilon greater than 0 there exists a partition P of a b such that its oscillatory sum UPF minus LPF is less than epsilon. If and only if condition means you have to prove the theorem in two parts. First, suppose f is Riemann integrable and prove that UPF minus LPF is less than epsilon. That means, first suppose f is Riemann integrable on AB. Then you have lower integral a to b f of x dx is equal to upper integral a to b f of x dx is simply integral a to b f of x dx. Then for any epsilon greater than 0, you have UPF is less than upper integral a to b f of x dx plus epsilon by 2 and LPF is less than lower integral a to b f of x dx minus epsilon by 2. Just now we stated by using Darboux theorem for any partition P with norm P less than delta. So, what you will have, your UPF is less than integral a to b f of x dx plus epsilon by 2 by our assumption that f is Riemann integrable, and integral a to b f of x dx is less than LPF plus epsilon by 2. That means, combining both, you subtract from one another, you get UPF minus LPF is less than epsilon. That means, whenever the function f is Riemann integrable, we have UPF minus LPF is less than epsilon. Conversely, we can prove whenever UPF minus LPF is less than epsilon, we can prove that upper integral a to b f of x dx is equal to lower integral a to b f of x dx. That means, how you prove? You have upper integral a to b f of x dx is infimum of UPF. So, what do you mean by that? Infimum is less than or equal to element. So, upper integral a to b f of x dx is less than or equal to UPF. In the similar manner, you have lower integral a to b f of x dx is greater than or equal to LPF. So, you have upper integral a to b f of x dx minus lower integral a to b f of x dx is less than or equal to UPF minus LPF, which is less than epsilon. That means, upper integral is equal to lower integral. Therefore, f is Riemann integrable on AB whenever you have UPF minus LPF is less than epsilon. So, in this lecture, what we have done is, we defined what is infimum and supremum, and infimum is a greatest lower bound, supremum is least upper bound. We have constructed, we have defined upper Darboux sum and lower Darboux sum or Riemann sums, and we proved that set of all lower Riemann sums LPF is bounded above and UPF is bounded below, and we derived the necessary and sufficient condition for a Riemann integrable, for a function to be Riemann integrable is UPF minus LPF is less than epsilon. Thank you.